Alright, good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. And we're going to be doing some more math communication tonight. We're looking at three particular papers, at least for now. See how far we actually get in any of them. Okay, swap locations of those. Cool. So we have here, X plays Pokemon for almost every X. So, my understanding for this one that I've just kind of poked in for a minute or so is that when we're looking at almost every number X that exists out there, we know that most of these numbers are going to be, or literally almost every one of those numbers are going to be transcendental numbers. And because they're almost all of them, transcendental, we will notice that they do not have any discernible pattern. And as such, every single one of them, every single one of those transcendental numbers should effectively be able to play Pokemon and win eventually. Eventually is doing some heavy lifting here because it is going to be like literally nearly impossible for any individual person to end up surviving long enough to actually see it, let alone the game console that you're using.
Hello there.
So, we start with C. Evans Hedges, abstract. This paper provides a brief write-up showing that for any finite state game, a disjunctive number x will eventually win that game. The proof techniques here are well known, and this result follows immediately from folklore results in automata theory. This short paper primarily serves as an expositional piece to collect this proof with the fun context of Pi plays Pokemon serving as motivation. In October 2021, the Twitch channel Winning Sequence began streaming Pi Plays Pokemon, where each number 0 through 9 was mapped to a Game Boy Advance button, and Pi began playing Pokemon Sapphire at 1 digit per second. As of writing, Winning Sequence has played for just over Pi years. That was December 29th, 2025. Has pushed over 100 million buttons, and despite having never left the starting area, has a level 90 set tile. This naturally leads us to question, will Pi eventually win Pokemon? Although Pi is suspected of being a normal number. Citation 1. Amicable Numbers, les probabilités des nombres et leur application arithmétique, rendu del ciclo matemático de Palermo. Okay. We're not going to be able to read that one, but... Oh, 1909. Okay. So, well documented. We do not know if this is the case, and unfortunately because our lack of knowledge of properties of pi, we are unable to answer this question at present. However, we are able to show that for any disjunctive number x, disjunctive numbers, Christian Escarod and Tudor Zamferescu, Disjunctive Sequences, a Probabilistic Approach, Discrete Mathematics, 1998. Which is Lebesgue almost every number, X will eventually win Pokemon. The theorem is stated for any finite state game, with finitely many actions that can be taken at any point in time. It also extends to games with deterministic pseudo-random number generators and holds with probability 1 for games with true random number generators. This result follows from a well-known result in automata theory 3 and 8, and this paper aims to be a fun introduction to how graph and wow. Aims to be a fun introduction to how graph and automata theory can be used to model games that we might find interesting. So, 3. Janczeni Poznamka ke... No, that's... I want to say that's Hungarian. 1964, and Mikhail Volkov, Synchronizing Automata and the Czerny Conjecture, from number 3, Language and Automata Theory and Applications, page, 2008. Okay. Now that I'm over here, the other thing I might want to do is look up that channel on Twitch. Winning sequence. Oh, currently live. Imagine that. Okay, as of 19 January 2026, 23:25 Central European time, looks like. So, yeah, current. Okay. If anyone happens to be interested in this, run this in the background forever. We have twitch.tv/winning sequence, and we have our X plays Pokemon paper. So if anybody is interested in watching that one. They appear to be doing a lot of moving back and forth, so, and then opening the Pokedex and closing the Pokedex. Oh no. Okay. In order to model these finite state games, of which all computer games must necessarily be due to memory constraints, we start with a collection V of possible game states. If the game additionally uses a pseudo-random number generator, PRNG, from a single generated seed, we may also include in V the current state of the PRNG. Thus, given a state of the game V in the set V for any given button push B, V will deterministically transition to some V prime in V. We then say there is a directed edge from V to V prime with label B. Let E, epsilon something, denote the collection of all edges for a given game. We then say the game G is the graph G equals VE or V epsilon. In this sense, a game contains information about the state of the game as well as the possible transitions between the states. Note that this kind of game is deterministic since we have embedded the current state of the PRNG into V. So, I have done something like this. I don't know if it was here on this screen, but we talked about Turing machines at one point. And it's going to be a directed graph of all possible states and outcomes. Given a certain current state, what are the possibilities? So, for instance, given a current state, let's just call this start. Like the start of the game, right? The A button, for example, will end up putting us into a new state. So this is like right. Actually. Right, so let's even be more specific. We're going to be in the state start conversation, and then the button A, and possibly the button B as well, will move the dialogue forward. And then, for instance, A and B are going to continue moving the dialogue forward until we reach a state at which we're, we reach an end point of that particular conversation. This might be a terrible use of the, or filling in of the actual blanks, because I don't think it necessarily will happen for this outcome, but nonetheless. Right, and then once we get beyond the dialogue moving forward, then we're also going to see states which include like movement, in fact, that's a terrible idea. Let's not do that. What are the possibilities in terms of... It's not the action of moving the dialogue forward, it's going to just be the state of being in the dialogue itself. And it won't be necessarily right. Let's say that A and B advance dialogue. It's going to check end, and then if the answer is no, then it just continues back cycling through. If the answer is yes, right, reaches the end of the dialogue, then we're in the state where we can do like the world map. At which point we have stuff like right, any of the particular directions, up, down, left, right, doesn't really matter. It's going to check collision. Yeah, and collision can be with an actual object, or it can be with events. So again, this is like if no, then we just end up back here. If it's yes, then we go to some action state. And it'll determine what exactly did it collide with. So it'll say like, okay, if there is, if it's just with like an object. Hey Famish, how you doing? If it's just with an object, then we go back to the world map. Nothing happens, it's just that your character doesn't move. So if there's no collision, it's no and move. Again, if it's yes, we have the action state. If it's the object, then we don't move. But if it's like battle, then we engage. We end up in battle state. And there's a number of different things you could do. So one is to, run whatever button combination that is. There's also like doing battle, so it's going to be our whatever the button is that we've got here is going to send us into an action state. I believe there is like one button if we do cancel, right? If we do B, for example, it does literally nothing on this particular screen, so it's not going to do anything. So this is a rudimentary design of what's called the Turing machine, where you have your directed graphs of your states and your outcomes, which are shown. Your inputs are going to be like the things that you're writing above the arrows, and the directed graph is showing you where everything is going to. What state did you start in? What state did you enter? Okay, so this is all about number plays Pokemon for almost every X. So whatever X you've got, whatever X you use as a normal number, with those particular definitions. So it is most likely going to be transcendental numbers, and probably also including a lot of the like square root, cube root, non-repeating values. So square root of 2, for example, should be a normal number. I don't know what the exact definition is, but we can find out in a little bit. And C. Evans Hedges says, well, if we plug in, almost any number in for x, as long as it is a normal number, then in theory, that number should be able to complete Pokemon, given asterisk enough time. We also found that winning sequence is a Twitch channel, which is currently doing Pi Plays Pokemon, specifically Pokemon Sapphire. Currently has a level 33 Beautifly here. And once every second, right, Sceptile is the level 93? 98? I can't tell. Every 1 second, a random number is selected. Again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 as the randomly selected action that it can take once every second. Currently on digit number 127,195,474, 5, 6, 7, etc. of pi. So, interesting. At time of publishing, again, this was 29th of December, just this past month. What's that? 3 weeks ago. Note that this kind of game is deterministic since we have embedded the current state of the PRNG into V. If we did not, then we would have to include either sample transitions with the same label combined with the output of the PRNG. For this paper, however, we stick to the simplified case where V, again, our current state, V includes the state of the PRNG, and our game state transitions can be thought to be deterministic. We note here that this is the case for classic Pokemon games, including Pokemon Sapphire, which uses the linear congruential generator, LCG, with a period of 2 to the 32nd. Thus, the state space V is effectively the product of the memory's game states and the 2 to the 32 possibility states of LCG. We also say that a path in the graph G is a sequence of edges E1, E2, all the way to e to the k that traverse a sequence of vertices V0 through Vk, where the edge E sub I is an edge from V sub I minus 1 to V sub I. For a given graph G as described above, the word W is called synchronizing if for any two starting vertices V1, V2, we traverse the path of edges generated by W, i.e. the edges that are labeled according to the labels from W. The resulting vertex is the same, i.e. V1 maps to V along W, and V2 maps to V along W. Finally, a vertex V is called a sync state if for every possible edge E in E, epsilon, whatever, that leaves V, E maps, that leaves V, E maps V to V. This means that once you have reached V, all future states of the game will be V, and the game is effectively stuck. In the context of gaming, these are referred to as hard locks. For the remainder of this paper, we'll assume that G has a singular sync state, V bar, arrow, such that for any V and V, there exists a path from V to V bar. In terms of the game, we want V bar to denote that you have won the game, requiring that any V in the game state space has a path to V bar, means that no matter what the current state of the game, it is possible to still win the game. This means that we are assuming that the game is win reducible. You cannot hard lock yourself in a state where winning becomes impossible. Finally, we consider how the button pushes are generated to play the game. For our given game G, we have some finite number of actions B that are possible. We denote these actions as symbols from the alphabet B, being 0 through B minus 1. Thus, we could take any real number x in the reals and examine base B expansion of x. An important concept for this paper is that of a disjunctive number. We say that x is disjunctive in the reals in base B if for any finite word 0 through w belonging to 0 through b minus 1 to the n, the word w appears in the base B expansion of x. We say x is disjunctive if it is disjunctive for every base greater than or equal to 2. Okay. Note here that Lebesgue, almost every real is a normal number, which is a much stronger property that requires a finite word to occur with the appropriate frequency. We do not define this formally here as it is not required, but we simply note that almost every number is disjunctive. Again, realistically, we're talking about transcendental numbers as an example, so pi and e and whatever. The issue is that all of those numbers, if you have gone along and expanded a certain number of decimal places of that number, whatever it might be, there are still an infinite number of numbers, an infinite number of possibilities to go. And then it's 10 raised to that infinite power, so I mean it's a much larger number in terms of the number of possibilities of future games. Let G be a game or graph as described above. Then there exists a synchronizing word W that maps all vertices to V bar, bounded above in length G squared. Quadratic bound G squared is a standard result, but it is worth noting the connection to the famous Czerny conjecture. The conjecture posits that for any synchronizing automaton with n states, there exists a synchronizing word of length at most n-1 squared. While this remains one of the most significant open problems in automata theory, the existence of some polynomial bound is sufficient for our purposes. Okay, that is 7. Jean-Éric Pin on 2 combinatorial problems arising from automata theory. Annals of Discrete Mathematics, 1983. Proof. First, we enumerate the states V, V bar, V1, all the way through V capital N, where capital N is the size of V minus 1. Okay. For each I for each I between 1 and n, there exists a winning word m sub I mapping v sub I to v bar. So your current state of the game, vi, needs to be able to map in some sequence, being the word. That'll get you to the end state. We construct the synchronizing word w inductively. Set w1 equals lowercase w1. After applying w1, the synchronizing word w1, we observe that v sub 1 is mapped to v bar. Since v bar is a sync state, any further inputs will leave the game in state v bar. Now consider v2. After the application of w1, the state v2 is mapped to some v sub I2. Let wi2 be the word that maps vi2 to v bar. We then set w2 equal to w1 lower wi2. By construction, w2 maps both v1 and v2 to v bar. Continuing this process for all n vertices, we obtain a finite word w equals w sub n capital, such that for every starting vertex, the game's state after application of big W is going to be v bar. Finally, we note that each w sub I can be chosen to have length at most v big V, or the size of big V. Thus, the length of W is bounded above by n size of V less than the size of V squared. Goodness. Right, so if we're assuming that every possible vertex will eventually reach the end state and not get locked in a different sync state, which hard locking is a real thing, and a bit of a tough problem to get around. They are a bit hand-wavy at this moment and saying, well, there's no hard locking in the game. We're just going to assume that it's not possible to hard lock, or in the given state, it knows where the hard locks are and will intentionally avoid them. So, if a particular value is picked and it will hard lock the game, then re-roll and try again. Right, so the size of V, if you are... Right, okay. The size of W, the size of the word that you can use to get from your current state to the end state, must be less than or equal to the size of the entire space that you have. Right, so... so here the number of vertices n could be multiplied by the size of your space that you're starting with. The value of V. Which must be less than or equal to, right, size of V squared. Right, because n is going to be less than or equal to V itself. While Theorem 3.1 guarantees the existence of a winning word, finding the shortest such word is significantly more difficult. It is a known result in computational complexity that finding the shortest synchronizing word for a given automaton is NP hard. Lovely. 4 and 6. David Epstein, Reset Sequences for Monotonic Automata, Siam Journal on Computing, 1990. And 6. Jan Olszewski and Michael Hummels, Complexity of Finding Reset Words in Finite Automata, Mathematical Foundations for Computer Science, MFCS, Lecture Notes in Computer Science, Springer 2010. Thus, while X will win eventually, a speedrunner, or particularly impatient real number, would find the task of optimizing this win sequence to be computationally intractable. Fair. Theorem 3.4. Let X be disjunctive, then X will win any deterministic game that cannot be lost. This follows immediately from proof 3.1. Let W be the synchronizing word that exists by theorem 3.1, since W will appear in X, and we know that W will win regardless of the current state of the game. It does not matter what X does before seeing the W. After completing W, we are guaranteed to win the game. Observation: if a game has B buttons to push, then we have B raised to the size of G squared sequences of length size of G squared. Again, that's the size of the game, the number of G be a game or graph as described above. So it's going to be the particular path taken, and if it goes back and forth a bunch of times, like we already saw with winning sequence there. Right, it is perfectly possible. If a game has B buttons to push, we got that. If we concatenate all of these, then we beat the game after a sequence of size of G squared times B raised to the size of G squared button pushes. This bound is horribly bad for real-world considerations, as Pokemon Sapphire has a save state of 1 megabyte, which means we can bound G by 8 times 10 to the 6th. Since it also has 8 buttons, we can win Pokemon Sapphire in 8 times 10 to the 6th squared times 8 raised to 8 times 10 to the 6th squared, which is 2 to the 6th times 10 to the 12th times 2 to the 3rd times 2 to the 3 times 2 to the 6th times 10 to the 12th, which is approximately 2 to the 10 to the 14th button pushes. This is a horrible bound. This number has about 30 trillion digits, and with there being approximately 10 to the 80th atoms in the observable universe, this number is effectively 10 to the 30 trillion times larger than that. It is simply large, similarly large compared to the number of Planck volumes in the observable universe. This bound is horrifyingly bad, and even though we can write 2 to the 10 to the 14th relatively easily here, it is an insanely large number for any practical purpose. As an additional fact we note here, that if we appropriately encode our game G to support RNG separately, so long as the RNG will show every word with some positive probability, then every disjunctive number X will win G with probability 1 with respect to the RNG. Let G be a game with random number generator. Let RNG have full support over the space of all words. If X is disjunctive, then X will win the game G with probability 1. Proof: let W be the synchronizing word from theorem 3.1. Let R be the required sequence of RNG outputs for which WR is guaranteed to win. Since the RNG has full support with respect to all finite words, the probability P of R greater than 0, and since X is disjunctive, we know W occurs infinitely often. Thus, for each occurrence of W, there is probability 1 minus P of R less than 1 that X will not win the game at that point. Since W occurs infinitely often, we know that in the limit, the probability that x will not win is going to be the limit as n goes to infinity of 1 minus p of r all to the n, which is going to be 0. Thus, with probability 1, x will win the game. Concluding remarks. That's not what I wanted. We've shown that for almost every number x, the base B expansion of x contains a sequence of button pushes that will win any deterministic win-reducible game. Because a disjunctive number contains every finite string, it will also necessarily contain the sequence of inputs for every possible tool-assisted speedrun, TAS, including the frame-perfect optimal playthrough. Assuming the buttons are pushed at the appropriate speed for said frame-perfect optimal playthrough. However, as shown by the bound in observation 3.1, the result is purely existential. The length of the guaranteed winning sequence for a game as complex as Pokemon Sapphire is so vast, it exceeds the number of Planck volumes in the observable universe by many orders of magnitude. While a disjunctive number x will win eventually, it is almost certain that the physical hardware running the game would succumb to the heat death of the universe long before the winning digit is reached. Thus, while pi likely contains a winning playthrough of Pokemon, it is sadly quite possible that the universe does not contain enough time for us to witness it. Nice. Right. Anybody have any questions on that? Let me know. From 26 December 2025, amicable numbers and their connection to the Euler Totient function. I have attempted to read about the Euler Totient function multiple times, and I keep getting lost in some of the maybe more silly aspects of it. So we'll see how it goes. Amicable numbers and their connection to the Euler Totient function by Eli Reza Mavadat and Saeed Alikhani, December 30th, 2025. Interesting. Independent researcher from Mashhad, Iran, and Yad's University. Abstract. A pair of numbers is amicable if each number contains the sum of the proper divisors of the other. So, if a number contains, or if a number has proper divisors whose sum is itself, that is perfect, and then if they are pointing at a different number mutually, then then those are going to be amicable, an amicable pair. And since the sum of the proper divisors of a particular input number is going to be a single output number, this is going to be a function. So there's no possible way to get multiple values given one input. So this does exclude the possibility, I'm just thinking to myself here, this does exclude the possibility that you could have one number that's amicable with more than one other number, right? It's only possible to be amicable with one other number for any given input. After exploring the history and evolution of amicable numbers, introduces a novel characterization of amicable pairs whose greatest common divisor is a power of 2 using their distinct prime factorizations. Specifically, we determined pairs of the forms a equals 2 to the n ab, b equals 2 to the n cd, a equals 2 to the n abc, b equals 2 to the n de, and a equals 2 to the n abc, b equals 2 to the n def. Okay, so whether they have two or three proper factors, aside from the power of 2. From these configurations, we establish explicit symmetric identities that relate the sum phi of A plus phi of B of Euler's Totient functions directly to odd prime factors of A and B. Alright, one of the most remarkable sums in number theory is the aliquot sum S of n of a positive integer n. Yeah, I should have read a little bit further because it tells you exactly what it is. There's a name for that thing. It is the sum of all proper divisors of n, that is, all divisors of n other than n itself. So therefore, S of n, the aliquot sum, is equal to the sum of all d divisors, where d divides n and d is less than n, strictly. As usual, sigma of n is the sum of all divisors of n. Thus, sigma of n is going to be equal to S of n plus n. Right, okay. Yeah. So the aliquot sum is going to be the sum of all proper divisors, not including n itself, and then n is going to be added in to get us sigma of n, the sum of all possible divisors. So it's just missing itself. As usual, the relationships GCD and LCM are greatest common divisor and least common multiple, respectively. Two natural numbers m and n are said to be amicable if sigma of m equals sigma of n equals m plus n. Interesting, right? Because each of them is going to be S of n plus n equals S of m plus m. Right? And if m equals n, then m is perfect. Also, smallest perfect number is 6. Smallest pair of amicable numbers, 220 and 284, was known to Pythagoras. Although more than 2,000 years have passed, it is still unknown whether infinitely many amicable number pairs exist. The first significant rule established for finding amicable pairs is attributed to Thabit ibn Qurra, 9th century mathematician, which is as follows. P equals 3 times 2 to the n minus 1 minus 1. Q equals 3 times 2 to the n minus 1. R equals 9 times 2 to the 2n minus 1 minus 1. And M, big M, equals 2 to the n times PQ. N equals 2 to the n times R. Using Thabit ibn Qurra's rule, only 3 amicable pairs have been discovered so far. The first pair, 220, 284, is attributed to Pythagoras. Pair 17,296 and 18,416 was discovered by Ibn Albana al-Marrakushi in the 13th century. Later, 17th century, Fermat announced in a letter to Mersenne that the numbers 18,416 and 17,296 are an amicable pair. The pair 9,363,584 and 9,437,056 was discovered in the 17th century by Iranian mathematician Muhammad Baqir Yazdi, though it is attributed to Descartes in European texts. Obviously, they didn't communicate very much between the societies, but nonetheless. They were roughly contemporaries of each other, and so it seems that Yazdi found it first, although Descartes probably discovered it independently. Okay, Evenkuras formula only yields results for n equals 2, 4, and 7. A fourth pair has not yet been discovered using this formula. In the decades between 1700 and 1710, the great Euler presented a list of 64 amicable pairs. It was later realized in 1909 and 1914 that 2 of them were not actually amicable. Euler provided a more general formula than Evenkuras' rule for finding amicable pairs, and in fact, Evenkuras' formula is a special case of Euler's formula, which is as follows. Good evening and welcome everybody. Coming on in from Zach's channel. Hope y'all are having a great evening. We are looking at amicable pairs of numbers, and specifically, we have been rated. That paper there from arXiv. Amicable numbers and their connection to the Euler Totient function. We were just looking at the Euler formula in order to find amicable number pairs. And here it is. All numbers P, Q, R must be prime. So a number 2 to the n times PQ and B equals 2 to the n R, where P, Q, and R are defined as the following powers of 2. Nope, sorry. The following, I guess those would be Mersenne primes then. Right, they are a... No, it isn't. Never mind. Wait. Yes, it is. It is. Right, all 3 of these are Mersenne primes because they are all powers of 2 minus 1. Start using Pomodoro technique more? I mean, if it works for you, great. I did see somebody who, like, is more professional than I, who was like, look, if it works, great, but honestly, it's kind of performative. 45 minutes of studying with 15-minute breaks. Yeah. And again, if it works for you, great. You can focus without it, but as easy as you focus to forget. Yeah, that's another issue. For anybody who does not know me, my name is Obi-Wan Pez. This is N Simplex Pachinko. We do mathy type stuff on Mondays and Wednesdays. Currently, we're working on Math Communication Mondays, so we typically look up some papers on arXiv or something we might have heard about in the news and come and check it out and see what's up. Try to explain it as best I can. I only have a master's level understanding of most of the mathematics that I did, and there is a lot of mathematics out there. So we try to learn something new and try to explain things. If there are other people around, like any of you, who know something about the particular topic that we're talking about, then I would love for you to correct anything that I'm talking about. Or if I get stuck somewhere, again, please feel free to correct or try and teach me what's going on. We were just talking about the paper X plays Pokemon for almost every X. There is a Twitch channel called Winning Sequence, which we popped into over here, which is literally playing Pokemon Sapphire based on the digits of pi. So if you see down here, they're inputting 1 digit of pi every second into this controller mapping here, and it then goes through the digits of pi. It's performing a bit of a random walk at the moment. It's pretty much stayed within like this block on the screen as far as I've seen, in, today. But Energy to Hampter. Good evening and welcome. So anyway, yeah, we took a look at that paper, which does come to the conclusion that literally every, or nearly every, normal number which exists, which has an infinite number of non-repeating digits, and it has a couple of other caveats in there, but basically every single one of those, of the infinite numbers there are, will eventually complete any finitely sized game. So, whatever that might be. Can I teach you probability theory related to finance? That's a good question. Are you looking for anything in particular? Are you saying just stock portfolio manager? Do I know what you'll need to know? No. Realistically, we toss our money into a bunch of mutual funds that have good long-term stability and let it ride. At the moment, politics is making for an interesting play on our money. We'll see how that goes. But if you're talking about stochasticity, okay. So I did not actually take the stochastic methods class, and I know a little, but I'm gonna have to look stuff up. But the idea is that you're going to be looking at having a kind of a repeated path through a probability matrix. So you're going to have something that looks like this. And then you'd have an initial probably going to have some sort of initial matrix, which is like A. This is our P matrix. And so this would get you a P, and then doing, oh, that's a Markov chain, I guess. So when you're doing A times P to the N, so you just repeat the action over and over and over again, and a lot of times this ends up in a steady state. So you'd have long-term, over time, what is the probability of any particular thing happening. Ads are about to start, so I'm going to stand up and stretch and go downstairs, probably grab a snack or something. And we'll be back in 3 minutes. Thank you so much, everybody, for coming. And be right back. Let me know in chat if you have any particular other questions, and I'll try and get to them. Thank you.
stay the night. Don't try to change my mind. Please don't stay the night. Almost knew what's right. Don't make me ask you twice. Oh, don't stay the night. Don't try to turn it to a fight. You know I love you by my side. Just don't stay the night. Almost knew what's right.
I was looking at my phone trying to figure something out, and I had a scowl on my face, and my phone did not recognize me, so. Let's see. Let's go with... the usual. Punish myself a little bit. Well, that boy appears to have lost his black paint. Left the top off of it. It's completely dried out. Well, that's what happens. And you don't take cleanup seriously. Righto. 20 approximately actual push-ups. One, two, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20. All right, 25. That's a record. Woo! Not perfect, but 25 of the best ones I've probably ever done. Or at least consistently. Okay. So you got 2-hour intervals and then a 20-minute break. So is that a 140-minute cycle? Or is it a 2-hour cycle? 120. For anybody who is not already friends with all the other awesome math people that we have, we have our list of awesome math streamers. We have Slim at Academy of Useless Ideas, Dr. Gold at Actual Education, Don Factorial, E.N. Stuckey, E to the 2i Pi, that's Zach. Those of you who came over, you already know Zach. Merriweather Remark, Penn Center, Phobostream, Physics and Depression, Talos Teaches, and the Tutor Wizard. Ah. Rather not do your actual breaks at midnight. True. And our study groups. So if anybody is interested in learning any particular thing, you can go and talk with these people and learn with them. Rendeo, Math Spellbook, FizzBuzz, Suna Owl, and Walking Stick Library tend to do some sort of, hey, let's look at a particular topic, and then let's just learn it together. Okay. Alright, probability theory and related fields. Stochastic, random processes. Play testing on the side? Yeah. True. Alright. Phenomena that appear to vary in a random manner. Examples include growth of bacterial population, electrical current fluctuating due to thermal noise, or movement of gas molecule. Stochastic processes have applications in many disciplines such as biology, chemistry, etc., etc., etc. Seemingly random changes in financial markets have motivated the extensive use of stochastic processes in finance. Now, to your point, excuse me. To your point, Energy Dehamter, the interesting thing about a financial market is if you have a minimal stake in said market and like you're not fluctuating the actual market itself by your presence, then it could in theory have some sort of reasonable pattern that you might be able to figure out. Most likely you won't, just because of random fluctuations in the market and all these other things. But the problem ends up being the more of a stake you have in that particular market index or what have you, then it tends to end up messing with the very thing you're trying to measure. So it's in a little bit of a sort of similar way. It's a little bit like Heisenberg's uncertainty principle, right? You can, through the process of measuring the thing, you are going to reduce the your knowledge about either its current state or its trajectory. And again, the larger a stake you have, the more power you have to interpret the market, the less actual predictive ability you end up having because you are yourself affecting the market. So, there's all sorts of weird stuff going on. But when we look at so as we said over here, stochastic process, one of the simplest ones is the Bernoulli process, which is a sequence of independent and identically distributed, or IID, random variables. Each random variable takes a value between Oh. Oh, okay. Yeah. The test variables, the thing that you're trying to measure, have one of two possible outcomes, either P or 1 minus P being their probabilities. So that's what we were talking about there. It's not that they're... It says it kind of weird in the page that I'm reading it from, but you can find an idealized version of all this by repeatedly flipping a coin. For example, if a head the probability of obtaining a head is taken to be P and its value is 1, while the value of a tail is 0 with probability 1 minus P. Bernoulli process is a sequence of IID Bernoulli random variables where each idealized coin flip is a Bernoulli trial. We also have the random walks. So for instance, if you have probability P that you're going to break one way versus the other, for instance, the Liu-Hui triangle or Pascal triangle, if you drop an object into that pachinko board, if you will, hence the name of this entire channel, right down there, I guess. Right, if you have some sort of pachinko board in n-dimensional space, you have one of n possibilities that you could go. And for a simple Pascal triangle, it's either left or right. In other dimensions, we can have that be, vectors x1, x2, x3, all the way through x sub n. So it gets interesting very quickly. Vienna process looks at like Brownian movement in liquids. A sample path discussing the Vienna process is continuous everywhere but nowhere differentiable, which makes complete sense because there is going to be no sure way to be able to tell what the trajectory is of a particular outcome. So Brownian motion being the movement of molecules inside of hot teacup or coffee or something like that. You can notice it if you put a little bit of cinnamon in, right? It's typically not soluble, at least not very well. So if you watch its movement on the surface of the hot beverage as it just sits there, you'll notice that it kind of kicks around a little bit back and forth and all sorts of stuff. Poisson process has a few different forms. Often interpreted as a random set or random counting measure instead of stochastic process. In this setting, the Poisson process, also called Poisson point process, is one of the most important objects in probability theory, both for applications and theoretical reasons. But it has been remarked that the Poisson process does not receive as much attention as it should, partly due to it often being considered just on the real line and not on other mathematical spaces. However, it can be defined on n-dimensional Euclidean space or other mathematical spaces. Okay, so you have an index set of stochastic state space, a sample function, the single outcome of a stochastic process. So formed by taking a single possible value of each random variable of the stochastic process. The increment is the difference between two random variables of the same stochastic process. Law. A law of stochastic process X is defined as push forward measure mu equals P composed with X inverse. Function composition, yep. X inverse is the pre-image of measurable function. Okay. Seems like you could do a bunch of different stuff, again, with any particular stochastic process. This was one of the ones that I skipped in my master's program. I could have taken stochastic processes. But instead of doing that, I took differential equations, which was good for me, but is rather... It kind of defined where I was going, I think, with with these classes. So it kind of took me in more of a direction of the computer science neural networks rather than using Markov chains and other stochastic processes, understanding all of that, which I think I somewhat correctly anyway interpreted this as a lot more linear algebra than what I was interested in, which was differential equations. Yeah, whereabouts are you in terms of your education at the moment? Basic calculus, yeah. Some linear algebra, nice. Okay. So, most schools, at least in the US, are going to set it up kind of like, you know, Calc 1. Calc 2 is like integration methods, which also includes numerical analysis. The numerical analysis is going to be pretty awesome for usage in a lot of individual cases. After that, you have the big three, which are linear algebra, multivariate calculus, Calc 3, and differential equations. And those three kind of define like the basic idea of where you can go with this stuff. Stochastic methods was a second-year master's level class. So, like, I'm sure that there are undergrad classes on it, but at least, 15 years ago, my spouse and I had the option of taking those classes, stochastic processes, as a 2-class sequence in second-year masters. I think our combinatorics and like some other stuff in there. Combinatorics was a first-year master's class, which also means that it's probably cross-listed in senior level mathematics. So anybody who's a senior level math major probably would be able to take something similar to combinatorics, which is like the, basic probability theory. We did all sorts of stuff connected with graph theory and then some of the basic stochastic methods. we touched on like very little of them, but some. I remember being outside of a ice cream shop and having just gotten my my spouse and I were both in both like started up our master's programs, or that particular semester, both started classes on the same night, and then ended up getting getting our homework and stuff like that, and then taking our car and heading up to an ice cream shop. And like I was standing in line just doing day one of homework. I was just like, this is gonna be so awesome. So combinatorics I thought was a really cool class. No, that's not it. So in addition to like the Markov chain, right, all that's happening with this particular Markov chain is that we're taking P and just saying, what happens if we do this process over and over and over again? One of the ones that we did was something like, actually, it doesn't even have to be probability, right? This could be literally anything. So the categorization matrix in A here could very well be, we're talking like A1, A2, A3, A4. We're talking about a like disease matrix. The infected group is going to be over here. The uninfected is going to be over here. Let's see. No, that's not it either. Hang on. What are we doing? Right, so all of our matrices are basically like a miniature spreadsheet. So we're basically saying, like, what numbers of people might we have? This is going to be like town A and town B. And then our probability matrix P is going to be like the rate of interactions. Between the townspeople. So like P1 is going to be the rate at which the infected and uninfected meet each other in town A. And then 1 minus P1 is going to be the rate at which they don't interact with each other, or the rate at which... Yeah, it's going to be like transmission rates and all this other stuff. Right, so there's a bunch of stuff like this that you can do. And so like what are going to be the eventual steady states of this particular system is going to be like, you know, how do people in each group end up in each different category. So how could A1 transfer to A2? How could A1 transfer to A3? How could A1 transfer to A4? You can work out different probabilities. You can work out different probabilities and the ways in which they interact with each other, and then by raising p to the nth power, you're saying just over enough time, right? As n goes to infinity, a times p to the n ends up becoming a, like, particular matrix. So it's going to one outcome at the end. We could actually look one up. It's probably a better idea than just me rambling about it. Yeah, there we go. That's not what I wanted. Grr. Pop something over to the side of my screen. There we go. Right, the SIR model is susceptible, I is infected, and R is recovered. Whether that person is actually literally recovered or just no longer part of the infected group and no longer part of the susceptible group. Yikes. It gets kind of rough sometimes. So we have dsdt is going to be equal to negative beta times 1 over n times s. di dt is beta times 1 over n times s minus gamma times I, and dr dt is equal to gamma I, and then n equals s plus I plus r. Okay, so we have here a system of differential equations that are able to come up with the appropriate groups, and using it as a... Come on now. Boo. want you to give me the Markov chain for it, punk. Yeah, you're not gonna do that, are you? Okay.
We got millions of reasons to let it all go. Hope we're not too broken.
Okay, so the way that he's doing this in this paper, if we discretize, then we're saying that ds dt is actually going to be s sub t plus 1 minus s sub t over t plus 1 minus t. So there is no continuous model, realistically, in terms of what we're doing. He's plugging this into Excel and just being like, okay, let's take this step by step by step, fill in a spreadsheet and fill down with all the individual values. So all this stuff here is just 1, so whatever. This then becomes, right, s sub t plus 1 minus s sub t, which is equal to that negative beta over n times s sub t. Moving s sub t to the other side, we get that s sub t plus 1 is going to be equal to, factor out s sub t, 1 minus beta over n times s sub t. So whatever our current number is, we're going to multiply it by 1 minus beta over n, and that's going to give us our next value of s. Similarly for the others, I'm not sure this is actually going to create a Markov chain, but whatever, it's fine. This is going to be I sub t plus 1 minus I sub t is equal to beta over n times s minus sub t minus delta times I sub t. Again, same deal. This is now going to make I sub t plus 1 is going to be equal to beta over n times s sub t minus, no, plus, parentheses, 1 minus gamma. That's not a delta, that's gamma. Gamma times I sub t. Okay, and then same deal here, r sub t plus 1 minus r sub t is equal to gamma I sub t, which means that r sub t plus 1 is going to be equal to gamma I sub t plus r sub t. And then n is always going to be, it's a constant, right? S sub t plus I sub t plus r sub t. So technically, we might not need a particular number or whatever in there for representing those. However, what we will have is that s sub t plus 1, I sub t plus 1, and r sub t plus 1 is going to be equal to the matrix using those coefficients that we just had. S sub t plus 1 is going to be 1 minus beta over n, and then it is not relying on I or r. I sub t plus 1 relies on s sub t and I sub t, but not r. And r relies not on s, but on I and r. R sub t. Right, multiplied by s sub t, I sub t plus 1, r sub t plus 1. Now, hey, got myself. Okay, so in this particular case, this is actually looking at the constants, beta, n, and gamma, because those are going to be constants. And so we have the, like, I guess, n, n matrix. It's going to be equal to this probability matrix here, which is, oh man, I was going to call it I for interactivity or whatever, but that doesn't work. I got too many I's in here. We'll just call it P. Probability of interaction, that sort of thing. Or probability of changing states. And then here we've got our also n sub t. N sub t plus 1 is going to be like the sum of all of those. So we put n bar here just to say, oh no, it's totally not the n value that we had right over here where it says n. That's just a number, right? This is a matrix of how it all breaks down. So put the bars on it and totally different. 100%, yeah. Okay, so t plus, and in fact, if we make this t plus n for like however many steps we want to go, this is going to end up being a left multiplied p to the n times n bar, or yeah, fancy n. N matrix with the serif. Right, so this would end up being our Markov chain. And based on the numbers that you get, beta and n and gamma, and our starting value of, usually s is the only one that has it, you could be like, well, we started somewhere in the middle. So like, you know, after day 3 we had this many infected people and this many susceptible people and nobody recovered yet. You know, we've just noticed that this disease is going on, but nobody's done with it. Now that is also an assumption. Things like this were going on all the time in COVID, right? Our family, for instance, a family of 4, had two adults come down with and start exhibiting symptoms of COVID on one particular day. I guess technically she started a little bit before I did. we were laid up on the couch for like 4 days. The kids were bored, but, you know, our son never exhibited any symptoms, and our daughter never exhibited any symptoms and tested negative. Our son tested positive at the same time that I did. Or like the next day or something like that. It was just kind of like, well, guess our family's got it now. This was summer of 21. So we made it an entire year and a bit before we finally came down with it. So anyway, this particular Markov chain, if we take the limit as n goes to infinity, then t plus n is going to be limit n goes to infinity of p to the n times n sub t, big N, or vector n sub t. I guess that's also a point, right? We could just make these vectors. Right, this is going to be our steady state. And realistically, in this particular case, it's not even like a probability necessarily, but it ends up becoming a probability in the ways that it's being used, in the fact that there's only, you know, ones in certain places. If you sum them up, right, you get beta in the... No, you get 1 in every column. And each row is different. But if you were to sum up all the rows, you also get 3. Right? It's a 3 by 3 matrix. We end up getting just 1 for the total of... average total of each of the rows. And literal 1 for each of the columns. So if we did this with, like... let's see... Where is... Do I have Octave up? Doesn't look like it. Yeah. Octave Online. Ugh. Projectile. Right, so if we were to unlock... Right, pop that up so you can see the command line there. If we were to make n equals a... Let's just check here. Yep, cool. So if we make n 1,000, like, I don't know, 10, probably ridiculous, but it's fine. And 0 at the beginning. So 1,010 people who possibly have this particular infection, whatever it is. We'll let our alpha... Let our beta... 0.1, and our... Gonna need therapy with this freaking ads popping up. And gamma equals, let's go with 0. Let's just also do 0.1. And then we let our P be... that was 1 minus... So if we want to, like, I could hard code numbers in, right? But let's be realistic about this. So this was beta over sum of n. Okay, and then going across was 0 and 0. Then, next line down, semicolon, we're going to have beta over sum of n, comma. This was, what, 1 minus gamma? I'm going to drag this back over here. Right, beta over n, then 1 minus gamma, just 1 minus gamma. And then 0. And then last line is 0, gamma, 1. A. Okay, so now what we do is we say, let's do p times n. And we get this. Right, so technically it should probably round. But at the same time, if we round, we're going to get... yeah, okay. Int. No, we want it to round to 0 decimal places. No. Okay, so it does not want this to be any of that. Okay, there we go. So, because if I do p to a power, then it's not going to round it in between, but it'll be fine. So if we do like p times answer and round, huh. Touche, we have 5 extra people now. Oh no. Alright, terrible idea. So if we just do p times n, we're going to do p raised to the 10th times n. This is what the group now looks like. Well, actually, very sad. Alright, if we do 100... Hey, there we go, it's starting to move. Now we have like 1 person on the infected list, and it's possible that this is just going to die out. So we won't have any issues. If, on the other hand, we have beta equals 0.5, and then we do the same thing. So p raised to, well, p times n, just to see what happens. After the first one, we now have effectively 10 infected people right off the bat, or 9 infected and 1 recovered already. Okay. P to the 10 times n. We're still having the same problem here. That did nothing to change it at all. Beta equals... Oh, I didn't redefine... let's go back up to p, when I defined p in the first place. Right, much more interesting. So now p times n is going to get us... Yeah, no wonder it was... Okay, and then we do p to the 10th, so 10 possible interactions. Now we've got 995, susceptible, 6-ish people who are infected, and 8 who have now recovered. And if we go to 100, now we have 951 who are susceptible, 5 who are infected, and 53 who are, yeah. Okay, so if we go back and we take beta 2.8, and gamma 2.05, and then redefine P, and then try again, P times N. Yeah, so 10 infected, half a person recovered. So now we do to the 10th. Yeah, so now we're going to have more people in the infected group as we move on. That seems to be calming down a bit. Yeah, there we go. So ideally what's going to happen in the SIR model is that eventually everybody who is susceptible is going to eventually get it and then end up in the recovered group. Yeah, like that. Right? This is effectively 1010. This is effectively 0 on each of these. I mean, 0.36, but give or take. So that's the idea, is that now everybody's been put into the recovered pile. You've got effectively everybody in this particular steady state, right, is going to be 0, 0 R sub t. So actually, right, that's not even R sub t now. It's just n. Okay. I'm going to go back downstairs, grab, well, put the dishes away or whatever, but I'll be back in 3 minutes. Thanks everybody for coming. If you have any more questions, let me know. Drop them in chat, and I shall return shortly. Thanks so much for coming, everybody. Really appreciate it. And if you're interested, drop a follow. Tomorrow we've got blueprints, so look forward to playing more of that. See you in 3. Yeah, thanks for coming. All right.
Say I'm craving hope in this dark
A little bit of Tai Chi today. We'll say it all again once the Twitch people are back from ads, but... Alright, welcome back from ads. So we're going to do just a little bit of warm-up for Tai Chi, and then we'll do a little bit of Tai Chi, and maybe a karate form as well. Gotta keep up with fitness, woo! So, the warm-ups that we do for Tai Chi are mostly to get the joints moving and get fluid like equally distributed within the joints to make sure that they're actually doing the appropriate work they need to. And hopefully not grinding too much, because that would be painful. We're trying as much as we can to use natural movement and gravity rather than like trying to use muscle to push our arms around. So the first movement that we did with the arms kind of flinging in a windmill fashion, we're trying to bend into what's called the inguinal crease, which is that place between your thighs and your abdomen where there's like a crease into your groin. And like if you basically just lean into it and then push out of it, you'll notice that there's kind of a lot of give, and it allows you to do these kind of spiral motions. And a lot of power can be stored into the inguinal crease in order to do some serious damage, in order to like amplify the power that you end up putting into it and then taking out of it. That is essentially where most practitioners of Tai Chi consider the Chi to be, where like you're using the stored biomechanical energy in order to do something to amplify your power, which is not a magical Chi energy, but rather it is a biomechanical process that is like just very well known to practitioners. Right. We also do one that ends up like we reach really far back, come down, and kind of steeple the fingers, squat down a little bit, reach all the way back, straighten up, squat down. That was a mistake. And by doing a lot of these exercises, again, it keeps you limber, and there's a really great breathing exercise we do at the end of class, which ends up being like a lot of just kind of stretches. So we like reach up and then just pull, and then switch and pull, and then we do the like over the top thing where we stretch both ways this way, and then we do a breath in, breath out, breath in, and stretch down to the floor. And oftentimes, like right now, I can barely like get my fingers pretty close to the floor. But if you do it like 3-4 times in a row, you end up like stretching way further than you thought you could. I ended up putting all four extremities were flat on the floor. So my feet are already there. I got my hands all the way down to the floor and then started like pushing even further. I was like, wow, that actually worked. And then we come up and do a couple more just breaths. And then we get to the end of it and it's like, ugh, that feels really good. Especially when we were doing sets this past weekend here. We did a set of motions called Dalu, which is a two-person like combat form essentially. It's a little bit like one step, I guess, in karate, where like one person is just coming up and doing a strike to the face. So it's been a few months since I've done it on the channel, just because I kind of forgot. It's not like it's hard, it's just it looks silly because there's only one person here. But effectively we're coming from this position where we're our body is already back here, and then we step up so that our feet are not quite together but pointing more or less out and pretty even with each other, and you're doing a split or a strike to the face. Your partner then does the mirror, which is that they're going to do a ward off and block you, turn, and then the next step for them is a pluck, return to standing roughly in the same place, and then they do a effectively armbar, pull you back. I do need a little bit of room, but this should still work, question mark. I hate, like, knocking my kids' stuff all around, but they keep leaving it all in the middle of the room. So for Dalu, you do a split, strike again to the face, and then when your partner tries to pull you off balance, what you do is you step forward and diagonally left. This is effectively going to allow you to potentially throw an elbow, and then so you go here, we step forward. It's going to allow us to throw an elbow, and then we step forward and right and do a shoulder. So this is a shoulder strike that I do all the time. From here, the other person has blocked us and is now potentially threatening to poke us in the face with their fingers. So we will go back here with a ward off, then turn 90 degrees and come back with a what is that? That's pluck. So we grab their hand and move it this way, and then our other hand is going to be blocking whatever's coming this way. Oh, that was it. Yeah. Boy. I'm going to just kick this a little bit over. Nope, that's the wrong way. See what I'm saying? Yeah, so you go and do a split, step, shoulder. Now that you're here, they will do a split at you. So they're coming from this direction and doing a split this way. So we come back and do a ward off, and then grab, reverse your grip, grab their wrist, shift, turn, and then with the other hand we're coming through and then doing sort of an arm bar this way. Then, now that they're here, again, we're kind of threatening them and saying, like, you don't want to put all of your weight into me because I'm just going to poke you in the face. Or worse. And then from here, you step forward and do the split. Step. Shoulder. Ward off. turn, pluck. Split, elbow, shoulder, ward off, turn, pluck. Pluck, roll back. That's that one. All right, split, elbow, shoulder, ward off, pluck, roll back. And so it's like this kind of flowy dance. And it works really well, especially with Tai Chi. I did this for like 5 minutes each with my instructor, the lady who was there like last week, a couple weeks ago, and this other guy who is the UK sumo champion, national champion in his weight class. So like, I don't think I could. Oh, and he's a police officer. So So, like, I couldn't really ask for a more diverse set of partners in this because, like, my instructor is just good. The lady who is the lady's getting on, right? She's trying. She needs a little bit of help, and so like I have a little bit more experience just in martial arts in general, and helping her through it is also teaching me. Just like when, you're teaching anything else, it's a good idea to, if you're learning something, it's also good to be a teacher to someone else. So it helps. And then the sumo champion is like absolute iron. Like you just bump into his body and you can tell like he is just solid. He probably weighs about the same as me, and like it's just all muscle. doesn't have this going on. But when I was doing this, I would end up, doing the split, come and do the shoulder this way, and I would notice that like I'd be able to do this last step here. If you basically, instead of like trying to push your way into something, like make connection and then like, it's going to take forever to do stuff. But if you take this stance and then just let your body weight kind of go into whatever it is you're doing, that is a lot of momentum. And so it just like, it connected and then just kept moving. And he's like, ugh, like every single time I was able to respond to what he was doing. And then, you do the ward off, turn, pluck and split, or pluck and roll back. And like I'd be able to respond to his like absolute iron body. I could just roll with it. If we use the Bruce Lee quote, right? Be like water, my friend. I would just kind of flow around and with his structure. And then every time that he softened up to move something, I was just like, okay, now I'm going to be rigid. And I popped into positions. And then he would just constantly like take this hit and have to move back. And I was just like, I'm getting it. When it's just me and my instructor, like these one-on-one classes, which they're not supposed to be private lessons, but like, I'll take it. When it's just the two of us, it's, it works pretty well. He still is teaching me great things, and I'm still learning really well. But the problem is that there's nobody else to learn from. And having, especially those two people, right? Somebody that I can learn from and teach, as well as somebody else that I can like do the thing and practice a different body type and a different martial art. He knows sumo and now Tai Chi, and I know karate and now Tai Chi. And like it's just two very different styles. I mean, three very different styles now that are melding in different ways. So I have no doubt that he could just grab me by the back of the belt here and be like, I toss you. But nonetheless, the rules in which we're using Tai Chi at the moment, it works really well. Okay, and let's do the first third of the form, apparently. Alright, so we go from here, start from bear. Tuck, move sideways, straighten out, hands up. Breathe out. Tuck, and turn here on the heel. Switch feet, this one moves forward. What is that? Damn it. Wow. I've been saying it for the entire time here. What's the... Ward off. There we go. Ward off, and the backhand stays roughly where it is. We turn a little bit on the heel. And then here we tuck in just a little bit and ward off the other way. We're now going to move the back foot just a bit. And then turn again here. Roll back. Press. Push. We come back this way. Turn on the heel. Come around this way. Shift weight back. Turn. And single whip. Put everything out to the left. Shift and turn all at the same time. And then bring down, up, lift just gently. This is like the front leg is just barely touching the ground. And we want our hands to be here. And feet to be, right foot to be just off the ground. All the weight is on my left foot. And then we come down and cover and bring the foot back and then forward, out, and shoulder strike. That should be there. And then from here, we do a crane, which is the foot comes in, moves to the front. It now has almost all of its, or almost no weight, and I'm touching with my toes. We bring the hands up, and then they go like this. So this is a block. One is going up, and one is coming down and across this way. And this is to block, my instructor said, if you push, roughly speaking, here and here on the body of your opponent, right? Again, you're not pushing so much as you're like stepping into it and using your weight. If you push the hip and the shoulder at the same time opposite each other, right, that person is probably going to fall. And if you do it while you sweep a leg at the same time, now their weight, or now they're, first of all, the bottom half of their body is turning under. So if you turn here and push here, right, pick this up, push this forward, they're going to rotate around their center of mass. So they're going to go that way. So with that in mind, if somebody is coming at you here, they're trying to push your shoulder and push your hip, then the appropriate response is to kick these out that way. And we block the one coming at our shoulder, we come in and up like that. The one coming at our hip, we come down and out like that. And this was the move here is essentially crane drying its wings, I believe was what he called it. So, like the crane actually, and he said when he was in Malaysia, he actually did see cranes hanging out by the water doing this because they're trying to dry off under their arms and then cool off because it is really hot in Malaysia. Okay, so let's kick this out. And then we're going to go over to amicable numbers again. Got some time still. Okay, so the concept of amicable numbers has undergone various generalizations since the early 20th century. In 1913, Dickson, number 7, defined a set of natural numbers n1, n2, n3 as an amicable triple if the sum of n1 is equal to the sum of n2 is equal to the sum of n3. So again, all of the factors of n1, n2, and n3, which is equal to n1 plus n2 plus n3. Okay, aliquot sum function s of n is equal to sigma of n minus n, and then this relationship can be expressed as aliquot of n1 is equal to n2 plus n3, aliquot of n2 is equal to n1 plus n3, and aliquot of n3 is equal to n1 plus n2. Smallest triple satisfying Dickson's definition is 1980, 2016, 2556. Dickson also extended this definition to k-tuples, so however large a group you want to get, there is a way to find it. Later, Yanni proposed the alternative definition for amicable triples, requiring that 2 sigma n1 equals 2 sigma n2 equals 2 sigma n3 equals n1 plus n2 plus n3. This is equivalent to the system n1 is equal to s of n2 plus s of n3. So the factors of n2 and n3 have to sum. That's interesting. Have to sum to n1. They will then have duplicates if, well, they will have at least the number 1 as a duplicate. So they could be mutually prime, but don't have to be. n2 is equal to s of n1 plus s of n3, and n3 equals s of n1 plus s of n2. Under Yanni's criteria, smallest amicable triple is 238, 255, 371. Similar to Dickson, Yanni generalized to k-tuples. Other researchers explored multiply or feeble variations. Carmichael defined multiplicity amicable pair Mn, such that the sigma of m equals the sigma of n equals t times m plus n, where t is some positive integer. Okay. So they're amicable in that they're okay. They're amicable in that their total factor sum, right? Their total factor sum is the same as each other, which is then some positive integer times the sum of the numbers themselves. Interesting. Okay, further extended to k-tuples again. Mason further extended logic to k-tuples. In 1995, Cohen, Gretton, and Haggis introduced the concept of multi-amicable numbers, where the aliquot sum of each number is a multiple of the other, rather than the aliquot sum being the same, or aliquot sum being a multiple of the sum of the numbers themselves, or whatever else. Bishop, Bozarth, Kuss, and Pete introduced feebly amicable k-tuples. satisfying the sum of n sub I over sum of n sub I is equal to 1. Okay. That's almost like a... It's almost like a sum of probabilities being equal to 1, but it's not, but it feels a little bit like it. It isn't the same, but it echoes, right? Or it isn't the same, but it rhymes. Every standard amicable k-tuple satisfies the identity. For k equals 2, the smallest feebly amicable pair is 412. Okay, so 4 is going to be 124. So that's going to be 4/9. And then 12 is 1, 2, 3, 4, 6, 12. 1, 2, 3, 4 gets 10. 6 and 12 is 18, so that's 28. 12 28ths is 3/7. Ooh, that can't be right. Oh, I did say 7ths, didn't I? Yeah. So 4/7 and 3/7. Yeah. Okay, cool. I mean, I knew he must have been right. It was just a matter of getting my brain into alignment. And an integer n is considered amicable if it is a member of an amicable pair equivalent to the condition sigma of n minus n is equal to sigma of n. Interesting. Oh, ew, gross. Okay, so the sigma of the aliquot sum of a particular number the aliquot sum is the sum of the numbers not including the number itself. Alright, hang on. Sigma of... Okay, let's not do that. Give some space. Okay, sigma of S of n equals sigma of n. And that was just that, right? Not n1, n2, or... Okay. So let's just double check here. Let's try like... Well, hang on. What was the amicable pair from the beginning? Right, amicable pair 220, 284, damn it. Yeah. 220, 284. Alright. Let's do this properly. Okay. 1, 2, 3, 4. 8 is going to be 16. 60 is not divisible by 8, so that's it. 1, 2, 4, 5, 10. Definitely got 22. What are some of the other ones? Right, 22 and 10. 5 and... Okay, wait, hang on. 22 and 10 is going to be 2 and 11, which is 5 and 2. So 2 squared, 5 and 11. Different combinations. We got 2, 3, four possibilities, and the number of combinations we can make into 2 bins. Grr. I know how to calculate this. It's just not clicking at this exact moment in time. Okay, so 11. We can make a pair to make 2 or 4 or 5 or 10, or 4 times 5 is 20. Right, obviously. 20 and 11. Yep, cool. Okay, 44. 55. Is going to be 110. Okay, so S is going to be all those. Sigma equals S plus 220 itself. Okay. 284, slightly more challenging. All right, 1, 2, 4. 8 does not. 6 does not, because this adds to 14. Right, the digital sum is going to be 14, which is not divisible by 3 or 6 or any of those. So 3's out. 4, 5, 6, 7. 7 is out. 8 is out. 9 is out. 10. .264 is divisible by 11, but not 284. Okay, so we get 284, which is going to be just strictly in sigma, not S. Mm-mm-mm-mm. 142. 71. Ugh, no wonder. Gross. Alright. One, 2, 4. 71 and 104. Can't add 4. Add 100, subtract 6. 42. Can't add 2. Add 10, subtract 8. Gets us 220. Excellent. Alright, I didn't miss any. I could have just literally looked at this because it's such a small list, it doesn't matter, but I want to make sure. Alright, and then the other one. So, again, we could make a small list here, it's fine, but I just feel like using my abacus. Right, 1, 2, 4, 5, 10, 11, 20, 22, 40, 4, 50, 5 and 110 is 284. Excellent. So this is a Japanese soroban rather than the actual Chinese abacus, but yeah, that's fine. Obviously, the word abacus is Latin. I gotta check the Chinese word on that. Alright. So, yeah, this works. This sum is that. This sum is that. So then what is the sigma of that particular number? Right, the S gets us the other one, and the sigma of that one interesting. Sigma, oh, I get it. S1 plus S2, right? Yeah. Yeah. That's pretty cute. So sigma 2 is equal to 2. Yes. Sigma 2 is equal to S2 plus 284 is S1. Right. Okay. Just needed to verify that for myself, but okay. That's pretty cool. So so yes, we figured that out. Let a of x denote the counting function for amicable numbers up to x. In 1955, Paul Erdős proved that amicable numbers have an asymptotic density of 0. So the limit as x approaches infinity of a of x over x is going to be 0. Subsequent research has established increasingly tight upper bounds for a of x. Ooh. Huh. Currently best known bound is provided by Pomerantz 18. On amicable numbers, analytic number theory, 2015. A of x should, right, the counting function for amicable numbers. So how many numbers are there? So the counting function for primes is logarithmic, approximately. So that also means that the log n over n is approaching 0. But best known bound provided by Pomerantz, a of x is less than or equal to x times the exponential, e to the negative square root of the natural log of x times natural log of x. What kind of function is this? Alright, so x times e to the negative square root of ln x. Ooh. Times natural log of x. What are you doing that for? Fine. Alright, we got a lower value there. And then if we continue to look off to the right here, as we go to 50 500. Oops. Okay. Just keeps going, bending out. Every time we keep increasing by orders of magnitude, right, we're just gonna keep bending it over further and further and further. 10 to the 16, 18. Nope, just keeps going. Keeps bending and keeps bending and keeps bending, and it's worse than even a natural log just by itself. Because at least natural log like goes off for infinity, you know, and goes off for an infinite amount of space, time, whatever you want to call it. Alright, cool. Numerous studies have been dedicated to extending these concepts motivated by historical developments. This paper proposes new results of amicable pairs. We examine the prime factorization of amicable number pairs. We find that there is no consistent pattern defined for all pairs. Some pairs have 2 prime factors, some have 3, and others have power-based factors, etc. In this paper, we consider pairs that have a greatest common factor in the form of 2 to the n. Millions of pairs are known today through computer algorithms. No single formula generates all of them, obviously. It'd be really nice, though, if one formula generated a family, and another formula generated another family, because then at least we'd be able to figure something out. Let AB be the amicable pair, and 2 to the n AB equals capital A, and 2 to the n CD equals capital B, where A and B lowercase are odd primes. Then A plus B is equal to 2 to the negative n times capital B minus, Euler Totient function here, phi of A plus phi of B, all plus 1. C plus D is equal to 2 to the negative n times the quantity A, capital A minus Euler Totient phi of A plus phi of B, all plus 1. Define Euler Totient function as S equals phi of A plus phi of B. Variables x and y are defined by relations. A minus S equals 2 to the n x. B minus S equals 2 to the n y. We want to show that x equals c plus d minus 1 and y equals a plus b minus 1 using the property that phi of 2 to the n equals 2 to the n minus 1 and phi of p equals p minus 1 for prime p. Okay. Interesting. Phi of A is equal to all this stuff. Phi of B is equal to all this stuff. Okay. So defined, right? That's just what it is. To work stuff around a little bit, but you get there in the end. The sum S is equal to 2 to the n minus 1 times AB plus CD minus parentheses sum of ABCD plus 2. Substitute S into equation 1 from the top. Get all that stuff. So 2x is equal to all this stuff. AB minus CD, that seems familiar, plus the sum of ABCD minus 2. By definition of amicable numbers, phi of A equals phi of B. Nope, sigma. sigma of A equals sigma of B equals A plus B. For A equals 2 to the n AB, we have sigma of A equals the following. Setting sigma of A equal to A plus B, we have the following. Dividing step 3 by 2 to the n, we have this. Okay. Claim is that C plus D equals X plus 1. Substituting X equals C plus D minus 1 into equation 2, we have the following. Okay. Adding 1 to both sides, we get this. Confirms that the relationship C plus D equals X plus 1 and A plus B equals Y plus 1 holds when the prime parts of the amicable numbers satisfy the fundamental growth condition required for sigma A equals sigma B. Let us apply 2.1 to amicable pair, A and B given here. We have the following, yada yada yada. Relationship for 2-term and 3-term factors. Right. Have the following. By definition, sigma of A equals A plus B for A equals 2 to the n ABC. Okay, dividing both sides by 2 to the n, expanding the left side, rearranging to isolate DE. Euler Totient functions given by the following, multiplying their sum by 2 to the n negative n. Show the following. Substitute equation 5. Substituting expanded form of DE from equation 4 in this expression. Cubic terms, ABC, and linear terms eventually cancel out through amicable property, sigma of A equals A plus B. So this confirms the equality. Have sigma of A plus, nope, that's phi of A plus phi of B equals 182, 192. Since this equals that, blah, 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 yes, 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 cool. Relationship for 3-term factors is given here. Odd primes, it's the same stuff, just a different order. Let us apply that to these ridiculous amicable pairs. Check formula 6, left-hand side, right-hand side. Both 6 and 7 of theorem 2.5 hold exactly for the given amicable pair. So, yes, they work on a real pair of amicable numbers. That helps. Present new characterization of amicable pairs based on their prime factorization with greatest common divisor is power of 2 by focusing on pairs of particular forms. We derived explicit symmetric relations that connect the sum of Euler's Totient functions with the prime factors of A and B. Theorems illustrate how structure of prime numbers determines simple linear or quadratic expressions in terms of 2 to the negative n times all that, and 2 to the negative n times all that. Results reveal an underlying algebraic symmetry that is not immediately apparent from the definition of amicability alone. Based on the patterns observed in 2 and 3-term factors, we propose the following general rules for amicable pairs, AB, where A equals 2 to the n product as I goes from 1 to k of p sub I, right, all prime numbers, all the prime factors, and B equals 2 to the n product j equals 1 to m, j goes from 1 to m, of q sub j, so all of the prime factors of B as a conjecture. Case 4 and 2-term relationships for x and y are hypothesized as follows. Case symmetric 4-term for symmetric higher order pairs, relationship shifts to a comparison of their symmetric polynomials. In general, we think for any pair with k factor where GCD is 2 to the n, the variable x will always be a function of the k-1th and k-2th elementary symmetric polynomials of prime factors. These generalized patterns open a pathway for further theoretical exploration. We conclude that by noting, although millions of amicable pairs are known today, a single universal generating formula remains elusive. The prime factor-based approach introduced here offers a new lens through which to study these numbers, linking them directly to Euler's Totient function and elementary symmetric polynomials of prime factors. Future work could focus on the proposed conjectures and on extending the results to pairs with more than 3 odd prime factors, and exploring whether similar totient-based characterizations exist for other generalizations of amicable numbers. That could be fun. And this is a 24-page paper. I don't think we have enough time for that, so we'll hang on to this for next time. Let's see. Anything cool today? Monday, January 26th. On Arnold's and Pushkin's puzzles. I don't know what that is, but build boy's surface. The kit actually works. Several models have been made. Excellent. Geometric topology. Pushkin's puzzles stirred quite a bit of controversy and opinions of all kinds. Pushkinists and poetry lovers. French epigraph is translated into Russian as follows. Very helpful. Latter phrase is a bit of trolling the reader and archness on Arnold's part, since as a mathematician he founded most of his output on entirely rigorous proofs. Note, however, how in this ornate phrase, many subordinate clauses, Arnold used those a special kind, and perhaps with an undoubted parallelism to Onegин's florid lines. The pseudo-hidden, playful attempt to use a similar Pushkin style of writing only confirms Ilyushenko's remarkable insight that Arnold can be regarded as a Pushkin in mathematics. Helpful. It wasn't that she'd read him really, nor was it that she much preferred to Lovelace Grandison, but merely that so long ago she'd often heard her Moscow cousin, Princess Laura, go on about her special aura. Her husband at the time was still her fiancé, and against her will, for she, in spite of family feeling, had someone else for whom she pined, a man whose heart and soul and mind she found a great deal more appealing. This Grandison was fashion's pet, a gambler and a guards cadet. About her clothes, one couldn't fault her. Like him, she dressed as taste decreed, but then they led her to the altar and never asked if she agreed. The clever husband chose correctly to take his grieving bride directly to his estate, where first she cried, with God knows whom on every side, and tossed about and seemed demented, and almost even left her spouse. But then she took to keeping house, and settled down and grew contented. Yeesh. Anyway, how we doing? Hey, we're in a new area. Pokemon Sapphire. Right, let's go and find somebody. Let's maybe go hang out with Casey Snow Art. So, Casey. There we go. We'll head on over there. And we'll be back tomorrow with blueprints. So if anybody would like to come and check out and see how the puzzling is going, please feel free to come on in. If you do not have a clue about any particular puzzle, you can work it out with me. I will definitely allow that. If you know what a particular puzzle is, or what the solution is, or you've done it before, just, hang out in the back seat there, and don't worry about it. We'll get it. It's just going to take time. And then we'll be back on, tomorrow for that. Wednesday for more cracking the GRE, the math subject test for the graduate record exam. And then we'll be back on Friday for some more games. So, see you all later. My name is Obi-Wan Pez. This is Ensign Blake Spachenko. Catch you next time.